So this is how I do things in case you have not taken a class from me before. I do all the screen recording, except it's not recording, it is actually streaming. If you want to watch anything that I have recorded in the past, you can go to YouTube and just enter the name of the channel, which is Some Profs. So this may be the only thing you need to write down, assuming I don't have any technical difficulties streaming today, because you can now watch everything else through YouTube. So you just have to remember my channel name. So once you get there, you go to videos, and you will see all the recordings that I have done in the past. So I think I have recordings for 3 years or so, of all the screen recordings. So you can go all the way back to like 3 years ago, how I taught this class. Is that okay? So does everybody understand how to access recorded content of this class? Okay, it does not replace being here in class. I will still take roll, okay? Because only in class you can ask questions and interact and discuss stuff. The online stuff is really only there to help you in case you go like, oh, I can't remember exactly what text said about that one thing. You can just kind of roll back the tape and watch it again. So that's kind of the intention of the recording. All right. Any questions at this point? I'm seeing new subscribers right away, so it's funny. You cannot see it because all you're seeing is only one part of my screen, but I can see all the subscribers that are popping up. Interesting. Okay. All right, so once I get this out of the way, we can now start on the syllabus. So we'll go ahead and start with the syllabus of this class. It's broken up into 2 pieces. The first part is specific to this section, because in semesters that I teach multiple sections, the second part is the same. I'm also using the same second part for all of my other classes. So instead of having that replicated in all of my other classes, I just have it as a separate document. So this one is pretty easy to kind of go over. This is all pulled out of the schedule as well as my teaching assignment. So this part here, the first part, is coming out of the schedule. We do have 2 lab sections, so you might want to remember which lab section you belong to. For people who are adding to the class who are on the wait list, I cannot have everybody on wait list to go to the first section of the lab. There's just not enough room nor oxygen. Okay, so so we'll have to figure out a way to kind of send half of those people to the second lab. The second lab is not too bad. Okay, it starts at 8:30 and it ends at about 10 o'clock. Okay, well, if you think it's bad, okay, I have to do it all the way through 10 o'clock, right? So you guys can, if you are in the second lab, you can go, have dinner, rest, take a break, and then come back for the second lab. Okay, I think that's kind of cool. Okay, and also, by the way, I have office hours tomorrow at 8 a.m. and I bike. So I'm gonna bike back home at about 10 p.m. tonight, and then bike back to campus, arriving no later than 8 a.m. tomorrow morning. Healthy lifestyle. Okay, so the second lab is not too much. I can understand why most people want to be in the first lab. Okay, I do understand that. There's the description of this class. The course covers the organization and behavior of real computer systems as if there are not real computer systems. At the assembly language level, I didn't write this, by the way. Topics include the mapping of statements and constructs in a high-level language into sequences of machine language instructions, as well as the internal representation of simple data types and structures. So basically, this class gives you the X-ray vision ability into your C and C++ programs. Okay, so that you can understand what is behind the scenes, how my program actually runs on the computer. So the learning objectives is required to be in the syllabus, and that's why I'm going to write it here. So throughout the semester, we'll touch on all of these topics. And then here's the tentative schedule. Okay, I don't usually follow the schedule very closely. It's just kind of like a, reminder of what topics I need to talk about. So here it is. Are there any questions about this class at this point? Books? There are no books. I post all the material that you need for this class on my website. If you find additional material that you think is useful for this class, by all means, you can buy or borrow or make a copy of that material, as long as you respect the copyright of the material. Okay, but I don't have any books for you guys to purchase. Is that okay? No one is leaving just because of that? Okay, well, because self-publishing may not be a good thing sometimes. All right, so that covers everything that is specific to this class. So we'll move on to talk about things that are not specific to this class. There's also a syllabus presentation from past semesters, so you can watch that again. But I'm just going to go over some of the main points as quickly as possible, so we can start to get into the class content. All right, so this is kind of boring. I don't include pictures like many other professors do, so it's pretty dry. But at the same time, you can read this on your cell phone pretty easily because it's all text. Okay, you guys are not getting it. It is really long, as you might have noticed over time, the syllabi of many professors have gotten longer and longer. It is not my personal preference. It is required to be this long. So I'm going to talk about myself a little bit here. My name is Tak. Okay, my last name is almost unpronounceable, so you can just call me Tak. Is that good? Yep.
Can you spell it and just pronounce it once so I know?
In Cantonese, it is pronounced Ngao Yang, but in Ngao Yang. And Cantonese has many sounds that are absent in English and vice versa, so that makes the approximation kind of difficult. But you can just call me Tak. That's all good. And as if it is not bad enough, this is actually the British approximation, and that was done maybe 100 years ago or something like that. So they did not even make it close. They butchered it, yes. Probably unintentionally, but they did a very good job unintentionally. So here's my phone number, email address. My office is actually going to be CMC 404. It is the third cubicle. Has everybody been to the new office buildings, in the CMC? No? Okay, so the CMC stands for the Computer and Math Complex. It is to the north of the campus. You guys will know because, you have to follow me to the lab, okay? Which is in the CMC, okay? So room 404, has my cubicle in it. On Tuesdays and Thursdays, I can also be found in the Design Hub. The time is off a little bit. I have to fix that. It is actually from noon to 4 p.m. I can be found in the Design Hub. And then on Fridays, this is outdated. Did I forget to refresh it? Okay, let me give it a refresh here. There we go. It was displaying a cached version of the document. I just refreshed it, Control R sometimes does not refresh the cache, not enough. So sometimes you have to press Control Shift R to refresh not only the web content, but also the cascading style sheets and stuff like that. So this is up to date. I like this, much better. So on Fridays, I will be on campus in my office from 10 to 11 a.m. So is that good? Clear enough? Okay, you guys know where to find me? This is a pretty typical 100% face-to-face lecture and lab. Not much different from your other classes. You got some reading material. I don't really have a lot of video clips. You can watch the old video clips if you want to get an idea of what I'm going to talk about in the next lecture, or you can review and lecture by watching YouTube again. And we do have some interactive activities in the lab. So we'll get to the lab part a little bit later. Regular, effective contact and communication policy. This is actually required by the college. So the resources you can use to stay in touch with me or to ask me questions or to talk about things related to the class would include office hours. You can email or phone me, or you can also use Canvas to text me. Okay, so all of those methods will work. Time frame policy basically says within the work week, you can expect a turnaround time of about 24 hours. Weekends and holidays about times 2, which is 48 hours. Is that okay so far? All right. Behavior policy. This is kind of new. I kind of put this in here. Basically, the policy is only here to make sure that the classroom and the lab are effective ways for me to teach and effective environments for you to learn. So the first sub-policy has to do with unintentional distracting behavior, which includes chatting and making noise. And good thing that we are not in one of the classrooms in CMC. I got students who like to fidget, like shaking and whatnot. But because the floor of the temporary buildings is not really solid, so that vibration can be felt like 6 feet away from that person. And I have, as an instructor, I can actually feel somebody fidgeting, like out there. So that can be distracting. It was distracting to me. I can only imagine it can be, distracting to other students as well. So these are not really major offenses. I would just kind of mention that and go like, okay, let's not chat or something like that. The second category are things that are much worse, behaviors that can cause fear, intimidation, the feeling of being intimidated, and discomfort. So these are definitely not good. Okay, so they will not be tolerated. First day of class or orientation. So you guys are all here except for people who are just watching it on YouTube. So if you're watching it on YouTube and not being in class, I'm sorry, you're being dropped. Accommodations. If you require accommodations because of accessibility, you can contact our DSPS office. The phone number is included here for more information. So accommodations can also include different accommodations or different arrangements for taking exams. But I cannot do a single thing until I get the paperwork from the DSPS office. Any questions about this part? Nope. Okay. Excessive absence. 6% or more is considered excessive absence. So what it boils down to, if you skip all the math here, what it boils down to is you can miss classes up to twice per semester. The third time is going to be excessive. Is that okay? So people can miss classes without excuse, without reason, up to 2 times. The third time is going to be excessive. And with excessive absence, people can get dropped. So don't get there, okay? If you're sick, let me know so I can count you in and say, okay, sick. Okay, that's legit. That's a good reason that you're missing class because you don't want to spread that to all your friends. Okay, that's good. All right. Are there any questions about the excessive absence policy? Nope. Okay. So absences that I have to excuse only include sickness. So what if your car breaks down? It wouldn't start. Well, technically, it is not on the list of things that I have to excuse. All right? So that's why I have a section that talks about unexcused absences. So this is a short list of things that are included, but it's not extensive. So there may be many other reasons, such as I overslept, I took a nap in the afternoon, and when I woke up, it was 10 o'clock already. That would not be excused. Late policy, well, it's simple. No late work is admitted. So I'm not going to grade anything that is turning late, or at least they won't get points. There are a few cases where people say, okay, it's going to be late, I still want you to grade it. Let me know how I did in this homework assignment. Okay, I'll grade it. But there won't be any points added to the grade book in that case. So how do you deal with this kind of harsh policy? Yep, just turn it in on time. Is that okay? Most of the work that you need to do in this class has a due date of 1 week. So it's not like, when I took calculus, that was a long time ago, we had homework assignments due every class has homework assignment due from the previous class. And it was a Monday, Wednesday, Friday class. So on Monday, there will be assignment due on Wednesday. On Wednesday, there will be assignment due on Friday and stuff like that. This class has homework assignments that are due usually in a week. Okay, so there shouldn't be a whole lot of reasons not to be able to do it in time. Section 13 is kind of important. It has to do with academic dishonesty. And this is how I look at it. Academic dishonesty occurs when a student or participate in any activity to attempt to show possession of a level of competency, knowledge, or skill that is beyond the level of the student or some other students. Okay, is that okay? Do I need to clarify that sentence? If it's below, I don't care. Okay. It's only when it's above that it can be an issue. Now, if it's above and it's only because of luck, okay, let's say I give you a multiple choice test and you have absolutely no idea of the subject matter at all, and you just randomly pick some answers, and guess what? You're so lucky that you pick the right answer every single time. That's fine with me. It's only when there's an intent and doing something to get to that, possession or display of more skill beyond, the capability of that person, then it becomes a problem. But we can also look at it from the positive perspective, which is academic integrity. So this part kind of sums it up. The grade of a particular assessment, like a test or a homework assignment, of a particular student reflects the academic performance of the student and only of the student who turned in the assessment work, not of anybody else, at the approved scheduled time of the assessment, not late, so that's why I don't let people turn in things late, following all the rules of the assessment as well as general rules already discussed in the syllabus, and using only resources that are permitted by the instructor. Okay, so that's kind of the more positive way to look at it, okay, is, those are the points that someone gets, playing by those particular rules. Is that okay? All right. So if a particular resource is not listed and you want to know whether it is permitted or not, the best way to find out is to ask me. Okay, so let's say, all the exams are open book and open notes. And you say, well, is that really the case? Can I bring in like 3 different books with me? The answer is yes. Okay, so ask me first. Can I bring in a scientific calculator that can convert between bases, like base 2 to base 16? Well, ask me first. If I say yes, then you can use that calculator. If no, then you cannot use that calculator. Is that okay? So don't make assumptions, because assumptions can lead to problems. Okay, I'm going to skip the limits test here. The importance part is I kind of need to mention it. So why do you think I want to make sure that there is academic integrity? What happens when, yeah, I know. That's why there's the chair. But why is this important? What if I just turn a blind eye and go like, okay, so here's a test. I am just going to come back in an hour and a half. Why is that bad in the long run? Yep.
We learn nothing, and there's no real point to the class.
Well, some people may be honest, so they actually learn something, and their grade reflects how much they have learned and how much they have achieved. It's just that some people may not do that, right? That some people may be looking for a shortcut and did not learn anything. But they say, I just need a piece of paper saying that I graduated. But why would that be bad for everybody in the end? Yep.
They would be ineffective in whatever they're trying to do, which could cause problems for whoever they're working for.
Okay.
Fired, and
Well, it doesn't even have to go that far. Yep.
It degrades the quality of someone's piece of paper who actually did the test.
Yes.
So overall, if you go into an industry and you say you graduate from this college and people know, well, there's a lot of people that are academically dishonest, I might not necessarily trust that you got an A in that or whatever your grade was.
Exactly.
So that's more. It affects your ability to get hired later.
It affects the entire college. So let's just say that at ARC we have enough professors who don't care. Okay, I'm just here to get my paycheck. Okay, in fact, I'm not going to teach the class. I'm just going to replay all the recording from the past. I come here, I click a button, and I just kind of walk away for an hour and a half, and then I click another button to stop that video playback. Okay, but if you think about it, then and when it's time to grade, I'm just going to go like, I don't want any trouble. I'm just going to give A's to everybody. Okay, check, 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 check. After a few semesters, and people start to transfer to, let's say UC Davis, okay, and a whole bunch of people who got A's and B's and really good grades from ARC just started to fall apart after they transfer. Don't you think those professors at UC Davis would notice? And then when they notice, they would go like, all of these people, transfer students who couldn't continue over here, came from AR. And they'll look a little bit further and go like, they all came from tax class. And then here comes another student who got an honest A because that student actually studied despite me not teaching the class. Would it be fair to that student go like, okay, I cannot count you in because, all those grades from ARC, especially from tech, it really does not reflect anything? It wouldn't be fair to that student. So which part do you think is the majority? People who are honest. And frankly, I don't really care which part is the majority. There can be no student here who really cares about what they're learning, and I'll still be doing it this way. All right. Consequences, okay, you guys can probably think of, what consequences can happen, okay. This is a really useful document too. It's called the Student Rights and Responsibilities because it includes your rights as well. Okay, what if tech went overboard, okay, and he accused half of the class for cheating when they're actually not cheating? What can you do? And say, that's not fair, I did not cheat. I actually worked, to get a good grade in this class. You consult this document, find out how you can file a grievance, and say, okay, this is not fair. I need someone to look at this. Is that okay? So it's a really kind of important document. Classroom behavior expectations. So it's kind of the same stuff. I might have repeated myself a little bit here. How to attend lectures. Now, this type of class is a little bit different because things are getting recorded, which means, I don't think it's necessary for you guys to write everything down. Okay, especially when I type really fast, with programs, or when I present something, that's already done. Okay, I think there's no need to copy everything down. As you might want to check with me and make sure that the recorder is on, especially sometimes I forget to turn on the mic, so it becomes silent. So you might want to check that first at the beginning of a class. But you might want to focus your time and what you write down to be something that is not recorded, okay? Do you guys have a question? I mean, can I answer your question? No? Okay. So that may be a good way to kind of take notes, but things that are not actually on the screen. Your own understanding of the material, okay? You might want to write that down. Or if you think something is particularly important, instead of copying everything from the whiteboard, you might want to write down the time when I start to talk about it. This makes it easy for you to locate that part of the video when you're watching that YouTube clip. Is that making any sense? Okay. All right. So section 17 is really long. I'm not going to get into it. But what I can get into is I emphasize not on whether you can remember anything or not. Okay, that thing that I just mentioned earlier, that my test is open book and open notes, is actually true. Okay, so what will I be testing if I'm not testing whether you can memorize the syntax of something or factual stuff? Problem solving, but before you can problem solve, you have to understand the material. So I'm testing for your understanding of the material and also whether you can apply your understanding to solve problems. So if I present something that I solved in class and I ask exactly the same thing in my test, would that be testing your problem solving skills? So what can you count on? It won't be the same, and there will be something in the test that you may not have seen before. But based on the skills that you have learned, you should be able to solve that problem. Okay, so that's the kind of thing you can expect from the exams of this class. Is that okay? All right. So it's a different kind of studying to some people. So I'm just going to skip this portion here, because it has a kind of funny example here. And I can also, okay, this part is kind of important. This question is important, but before this question, there's a different question that is also important. And I don't know the answer to that question. How do you know that you're not fully understanding a particular concept? That's the question. How do you know? Yep. If you cannot apply it. But when you're in class and you're listening to me explaining something, there won't be a whole lot of time for you to exercise the application of a concept. Yep.
But if you cannot ask a question about it?
Okay. Or if you cannot explain that concept to somebody else. Okay. So those are all kind of indicators that you may not understand the concept correctly or understand it fully. I find that people who tend to succeed in my classes are the people who has that kind of internal standard of saying, yes, I got this. Or no, I think I'm still missing something. Let me talk to the professor in the office hour and clarify that. Okay? But I cannot really answer that question. I cannot tell you, oh, these are the steps that you can take to check whether you understand the concept or not. Okay? But the application is a really good one. If you cannot apply that, which means in the lab activity, if you're getting stuck, that might be an indicator that you may not understand the concept entirely. Okay? But it's an important one, okay? I just don't know how to explain my internal process, okay? All right. So problem solving can only happen after you fully understand the concept. What is problem solving? Other than what the phrase implies. Okay, all right. So it's kind of like, you have all the puzzle pieces in a box, okay? And I say, I want that as the product. Okay, but we only have these individual components. So my question is, how do you connect and configure these components so that the result, the product, can do that? That's kind of like a problem-solving analogy, okay? So you have to first understand each individual piece fully, but then you also have to kind of, in your mind, you have to be able to understand What happens when I connect this piece to this piece? What happens when I connect this piece to that piece? So in class, I will explain to you this piece would do this, okay? And then I'll explain how that piece works. I'll explain the other piece, okay? This piece will behave this way. This is the specification. This is the behavior of this piece. I may not explain the interaction between those two. But then the exam question will ask you about, the answer to the question in an exam can be based on, I need to connect this piece to that piece. Are you guys understanding the concept I'm trying to explain? Okay. Independence is also important when you take a class. The question to ask is, when do you ask another person? It can be me, can be a fellow student, can be a tutor, about something that you don't understand, okay? It can be a homework assignment, you're kind of stuck. So how long do you stay stuck, and how much time do you put into trying to solve that problem before you go like, this is not productive, I need to ask someone? That's the question. So let me give you some extreme cases, okay? So let's say you have a homework assignment that's due in a week. Very typical in this class. You read the question, okay, and you spend 1 minute on it. You couldn't get it solved. You go like, tack. I think that might be a little too soon, right? Or you spend 6 days, 23 hours, and 59 minutes on it. You got 1 minute left. You go like, tack. That might be cutting it a little bit too close. So the question is, when do you ask that question? When do you say, okay, I have tried every way that I could to understand this concept and to apply it, but I'm still getting stuck? What do you think? Yep, go ahead.
You have to be aware of like when you might be able to schedule time to get tutor or help,
Mm-hmm.
and at least know to pull that emergency break, so you still have enough time to schedule that.
Yep. Okay. So that's a good answer. You just have to plan for that time. So you basically have to say, okay, if I meet with tech or the tutor or another student and I've resolved the issue, do I still have enough time to get it done and turn it in? Okay. So that would be kind of like a good backup. Kind of like a good estimate of when to ask for help. Okay. So when somebody is going to help you, what kind of help are you going to expect? How do you want the other person to help you? So let's say you are stuck with a homework assignment, you're stuck with a particular concept, you cannot understand it, or you just don't know how to apply it, okay? So how do you expect the other person to help you? Yep.
Constructive criticism.
Constructive criticism, okay, that's good. Yes? Acting like a rubber duck. Okay, I like that, okay? Or the other person can be a questioner, okay? Instead of giving you the answer, that person will guide you to the answer by asking you additional questions, okay? So those would be constructive ways for the other person to help you. The worst is the other person giving you the solution. It's like, don't bug me anymore, this is the answer, and then just walk away. That would be the worst, because then you get the answer, and you can't even go back and say, okay, let me see if I can reconstruct the answer myself, because you're looking at it right there. Okay. All right, cool. Studying before class is just a standard technique. Just kind of read a little bit of what we talked about the class before, what we're going to talk about in the current class. That will give you, the context to understand the material in class, as opposed to going to class kind of cold and not reviewing the material. All right, so we're getting down to the grading part, and let me.
Are you going to provide the reading assignments?
Reading assignments is kind of general.
How do you know what to study before the next class?
So the next link, whatever link that is next to right after what I'm going to talk about. So typically at the end of the class, I would tell you I want you guys to read up to a certain point. Okay?
Tell us what the documentation is and you tell us how far.
Right. Typically just one module ahead of me is good. And I'll talk about what I mean by one module. Because I used the term module long before we started to use Canvas. So one module is just really one article or one writing, one document that I write. And they're all linked in from Canvas. I'll show you guys later. I think we can get to the class material today. So the grading standard is, I'm just using A, B, C, D, F, in my grades. A, in a short description means excellent, B is good, and C, believe it or not, is satisfactory/fair, okay? D is low pass, and F is fail. What do they mean, okay? So in terms of scoring, A means it's a perfect answer. I cannot be any better, okay? You gave me everything that I was expecting. Good means it is with some minor mistakes or omissions, but it's not major, okay, just a little bit. C means it has some major mistakes or many mistakes, depending on the count versus, how bad each one is. But it still shows sufficient understanding, even though it's incomplete, of the understanding of the material and the ability to apply the knowledge. D means it is insufficient understanding of the material or insufficient demonstration of the ability to apply knowledge. F means no answer, it's completely wrong, basically not worth any points. I'm not going to talk about these, you can read it. So basically with job evaluation, what type of people would get a job evaluation of an A, a B, a C, a D, and an F? Okay? I understand some of you may not have a job yet at this point, okay? That's fairly normal. But I bet you most of you have either written or read product evaluation from Amazon, right? So what kind of product deserves 5 stars, 4 stars, 3 stars, and 1 star? I use kind of the same scale, okay? Well, you already know the GPA equivalents of the letter grades, 4, 3, 2, 1, and a 0. So the percentage is really just the center point of those particular points. So if anyone, this is, okay, so the threshold to cross over from one grade to another grade is the midpoint between those two. So if you look at 4 point as 100%, 0 point as 0%, those are the centers of all the grades. 100% is the center of an A, 75% is the center of a B, 50% is the center of a C, 25% is the center of a D, and 0% is the center of an F. So the halfway between those points are the thresholds. So that's why to get anyone who's getting less than 12.5% is going to get a letter grade of F. I don't think anyone is going to complain about that. Anyone who's getting between 12.5% and 37.5% gets a D. Anyone who's getting between 37.5% and 62.5% is getting a C. That's it. That's what you need to move on. And you can always ask students who have taken my classes before, does that make it very easy to pass tax class? So kind of keep that in mind. The activities in this class include graded homework assignments. That's 20% of your grade. And then we have exams. There are 3 exams in this class unless there's another big fire with a lot of smoke and the college has to shut down. Okay? So the intention is the first exam is 20%, is about 1/3 through the semester. The second exam is another 20%, which is about 66%, 2/3 through the whole semester. And then the final exam is 40% of your grade. So yes, it is true that if you ace the final exam, you can get a C out of this class already. I mean, using the math here, right? 40 is more than 37.5. Do you want to wait until the final exam to pass this class, turning in nothing and flunk all the exams? Probably not. Question? Yeah?
Will efficiency affect your grade?
Efficiency? What do you mean by efficiency? Like whether the program is the shortest it possibly can be? No, I just ask for correctness. So you can give me a scenic tour type of solution. As long as it ends up at the same destination, it'll still be good. Yep. So I will also give you ungraded homework assignments. Okay, with a class this size, you can kind of imagine how eager I am to grade homework assignments. So occasionally, or more occasionally than usual, I can give you ungraded homework assignments, which means they're just like homework assignments. I'll tell you what your program or what your logic is supposed to do. We'll give you a week to work on it, sometimes less time, because it's ungraded, and then I'll talk about it. But since you're not going to turn in anything, you basically have to grade your own solution. You look at your solution, you look at my solution, you compare those two. Okay? If you can figure out, ideal case, they're exactly the same. Okay, well, you have some confirmation that you understand the material and you know how to apply the knowledge. They're not the same, but yours still gets the job done. Okay? You might want to look at the differences in that case and understand why the two different solutions or the two different approaches gets the same thing done. Okay? Your solution doesn't work. Okay, text solutions works okay, but yours doesn't seem to work doesn't seem to work in all cases. Then you might want to find out why your solution is not working. What if you cannot figure it out? Well, come to my office hours. Okay, show me your solution and ask me why is my solution not working in all cases if you cannot figure out why it is not working in all cases. Okay, so that's how you make use of these ungraded homework assignments. Any questions? That's the whole syllabus. I skipped a lot of parts. I mean, you guys are supposed to read the entire thing, okay? But I don't want to use the entire class to talk about it. Is that good so far? Are there any part of the syllabus you want me to kind of clarify or expand? Nope. All right. And we are done with the syllabus. This year I forgot to include the final exam time. Let's see what happens here. How many people do not know how to get to the final exam schedule and figure out when the final exam is? Okay. All right. This is the wrong semester, obviously. So as a hacker, I just look at the URL and go like, what if I do this? I got that. Now don't tell me you haven't done it before. All right, so this is a Tuesday, Thursday class. The lecture starts at 5:30. So you just look it up. Oh, can you scroll down a little bit? It's an evening class. All right, so 5:30 is our start time. It is between 4:30 and 5:55. This is a Tuesday, Thursday class, so our final exam is on May 21st, the Tuesday, from 5:45 to 7:45. Okay, so you might want to mark it on your schedule to make sure that that time slot is kind of blocked. Is that okay? All right? Cool. The nice thing about having everything recorded is I can tell the dean, if in case somebody complained and say, Tech never told me about the final exam time, I can roll back the tape and say, yes, on the first day I did talk about it. Now, if I say something that's false or wrong, that gets recorded too. So it's fair. It is a very fair system. It's just that I get the editing permission to the video clips. Has anyone noticed that I have edited ever of my video clips? Nope. I'm too lazy to do it. All right. So we got, okay, I will update this. Okay, let me do it right now. Nope, that's not how I edit it. It's a link. Okay, I'll fix that later. Okay, so there is a share folder to a Google Drive folder that you have access to from day one. We probably will not be using a whole lot of it until the middle of the semester. But for those of you who are curious and want to find out what it is and what it has, well, here it is. Okay, there are a lot of files in it, but you're more than welcome to navigate and kind of find out what's in the share folder. But we won't be using a lot of the material until later on. All right. So this is the first, so the material that you need to kind of read, the reading material of this class, they're all linked in Canvas already. So am I answering part of your question back there? Okay. And I follow this particular sequence of going over the topics. So if I'm on a particular module, you know the next one is going to be what I'll be talking about next. So that's how you can kind of read ahead of me. If I'm already at the end of one module, at the end of a class, you know I'm going to start on the next one in the following class. Is that okay? Okay. So this is the first one that we're going to start with. And all of my modules are equally boring with no pictures, okay? And they're all text, just talking, yak, 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 okay? This one talks about physical states, truth, numbers, and computers. Okay, so let's figure out what this is all about. Tell me what computers are. What do you think is a computer? What does it do? Sorry? Math, it processes, okay? It computes, right? Hence the name computer, okay? So when you're doing math, okay, what is math about? Numbers, okay? Well, it's about values, not numbers. A number is the representation of a value. What is the difference, okay? A number and a value, they sound about the same to me. Okay, what is pi? What is the constant pi? What is the value of pi? What is it representing? What is the meaning of pi, the constant? It's a ratio. What kind of ratio is that? Exactly. So it is the ratio between the circumference of a circle versus the diameter of the same circle. It's a ratio, okay? So that's what the value is. Then what about that 3.1415 blah, 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 blah? That's a representation. That's a number, okay? It is only 3.14 blah, 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 blah because we're using base 10 numbers. Okay, I can choose to use another base of numbers and represent it using a different number, but it will still be the same value. Okay, I can give you another example to kind of differentiate the difference between, differentiate the concepts of what a value is versus what a number is, okay? How much is a bag of rice worth? Okay? I don't know, $20 bucks, okay? 20 US dollars. If you're in Japan, how many yens do you have to pay for the same bag of rice? I don't know the exchange rate, okay? Let's say 100 to 1, okay? So you'll be paying, what, 2,000 yens for the same bag of rice, okay? What about in China? How many ren are you going to pay for the same bag of rice? The exchange rate may be about 8 to 1 now, okay? So you might be paying 160 ren to pay for the same bag of rice. Wait, hold on a second here. How does that has anything to do with assembly language programming? What was the topic again? Value versus number, right? So because I changed the units, okay, the number is different, but what stays exactly the same? What it is worth, what a bag of rice is worth. The value stays exactly the same. Okay? So those things are related. Okay, so computers are supposed to process, to compute, to perform arithmetic operations on values. Okay? We got that. But how does it represent those things? I mean, I know how I'm going to represent values. I mean, we are used to this, right? So I'm just going to open up a notepad here. It's called a mouse pad, but same thing. Okay. Okay. 10 stands for 10. Okay, in most cases. Okay, if the base is not spelled out, it is base 10. So 10 is just 10. It is representing this quantity. Is that making any sense? Okay. It can also be represented as 1010 in base 2. We'll talk about base conversion later in this class. Okay. So inside the computer, how do we represent the values? How do we represent values inside the computer? Lots of little fingers, right? Lots of little hands, and on each hand, little fingers. I don't think that's what you're going to find in the Intel i7 processors. What do you think computers have? Not bytes is a concept of us, but what do you find as devices? Transistors. Okay. So if everything inside the computer, that does all the active computation are transistors, there must be a way to translate the state of a transistor to values that we need to represent. Is that making any sense? Okay. But how does that work? Okay. So let's go ahead and check out this slide here. I'm skipping around, by the way, in my slides. So what we're going to check out, okay, I'll give you a brief history first. Before there were transistors and chips and stuff like that, there were vacuum tubes. And most of you have not seen a vacuum tube because most of you have not even seen an incandescent light bulb, right? you guys grew up with CFLs and now LED light bulbs, okay? A vacuum tube is kind of an interesting device. The way it works is really interesting too. The hyperlinks are only here for those who are curious. You don't have to click on the hyperlinks to understand, okay, what is a vacuum tube and how does it work and stuff like that. But for those of you who are interested, you can click that and understand it. Vacuum tubes are really cool except for a few things. Well, if you think vacuum tubes are bad because they're big, they consume a lot of power and stuff like that, what do you think is worse than vacuum tubes as components of computers? Yep. Heat. Well, heat is what is bad about vacuum tube computers. But in terms of a mechanism that we can use to implement or to make computers, what can possibly be worse than vacuum tubes? Now, after all, vacuum tubes do not move. They're not mechanical, right? So what about electromechanical computers? They are slower. They consume a lot more power, and they're also prone to all kinds of problems because they're mechanical. But they do exist just about, let me do my math here, 60 years ago. How many people have seen that movie, An Imitation Game? And you guys didn't name a electromechanical computer? That's what Turing had been working on in the movie, and historically that part was correct as well. So you basically have motors turning rotors, and then the rotors control the contact points from one end to the other end of the setup. Okay, that's actually how. Oh, by the way, what was Alan Turing doing in that movie? What was the purpose of the computer that he was designing in the movie? To crack encryption, okay? Encryption, and what was the name of the machine that was encrypting messages? The Enigma machine, okay? And what do you think you can find inside an Enigma machine? It's electromechanical. Now, it doesn't move, okay? What it does is a whole bunch of disks that can interconnect with the next one. And by changing the configuration of those disks, the permutation of what is inputting and what is it's outputting can now change. So when you press a certain letter on the keyboard, another key is going to light up. And it basically maps every single key on the keyboard of a typewriter to a particular key. It can be the same key occasionally, okay? But it's a one-to-one mapping. And that's how it does the encryption. So when you send a message and you want to make sure that even though people can eavesdrop what is being transmitted and you don't want them to actually understand the content of the message, what do? You type the message and then you take note of what lights turn on and then you transmit the lighted letter through the radio. Is that okay? So even though the Allies could receive the radio message exactly the same as the intended recipient, they could only get like garbled messages, okay, or messages that do not make sense, because all those words, all the letters are kind of like all over the place. On the other end, another person using the same configuration as another Enigma machine would type in the radio message, and then the code would reverse itself to the correct pattern. Is that okay? That's kind of how the Enigma machine works. So what Alan Turing was working on was an electromechanical computer that can emulate these Enigma machines. That's what he was working on. So by being able to emulate these Enigma machines, he can now try out all possible disk positions until he finds the one that actually cracks the message. That's what he was working on. Okay, so that's electromechanical, and then vacuum tube came along a little bit later, or at about the same time, and then after that we got transistors. Transistors came from the word resistor, but it is a resistor that can change its resistance, and therefore it is called a transistor. It's really kind of interesting, and this one we'll take a closer look because all computers today that we know of are transistor-based. The next level is going to be quantum. How many people have at least kind of looked into what a quantum computer is, okay? And what kind of future it can bring us? Why do you think quantum computers are going to be problematic from a certain perspective? Yep. Yep, because it can crack encryption really, really fast. Because encryption that we use today are based on prime numbers or factoring numbers. And using a regular computer that we have today, okay, those problems are difficult to solve. There are no fast way to solve those problems. But when you have quantum computers, you can do massive parallel processing, and what we cannot solve in hundreds or even thousands of years boils down to like 10 minutes. So every known encryption that we know that we use today is going to be obsolete when quantum computers becomes reality. Okay, so that's going to be the next stage. But we are not going to talk about quantum computers in this class. We'll talk about transistors. So what we'll do is we'll talk about transistors, and by this time, I think most of you are totally bored by my notes, right? It's just a whole lot of words, and then even more words, and then a few hyperlinks, and then even more words, right? So what we'll do is we're going to play with transistors, and we'll build a very basic circuit using transistors that is actually useful throughout this entire class, okay? And the program I'm going to use to do this, okay, if you're not old like me yet, okay, enjoy your eyesight. This is why I need this, because I can't focus closer. And you might say, but Tech, you're nearsighted. All you have to do is to take off your glasses. Yes, I can focus closer this way, but then I'll be smelling my computer. So That's why I need that. There we go. This is a computer that will stay with you for the entire semester. It is called LogicSim. Your lab is going to have instructions of where to look for it, how to download it, how to run it, and stuff like that. But since I'm going to use it for demonstration, so you might want to pay attention to how I use this particular tool. It's LogicSim, which stands for Logic Simulator. It allows you to build logic circuits and then quote unquote run the logic circuit, okay, which is really cool. So what I'll do is I'm going to pull off a few components. And I can never really quite remember where those components are. I think they're under wiring. There we go. And under wiring, there is transistor. And I'll just put one here. And then we'll magnify that. So this is a transistor, or the symbol representing a transistor. A transistor has three terminals, has three what we call ports. Okay, one port is here to the left, one port is here to the right, and one port is here pointing up. Okay, so there are 3 ports. They serve different purpose. So let's go ahead and name the ports first. And to make it clear, we can magnify this a little bit more. And move it to the center, like that. Okay. You see this arrow here? What the arrow does is it is always pointing from source to drain. And the symbol, or the letter S, is always used to represent where the source is. The letter D is always used to represent where the drain is. And then the one remaining is called the gate. Okay? So here's your gate, which is represented by, which letter do you think is going to be used here? G. That's right. Okay. So now you have a basic transistor. The gate is kind of like the handle or the control of a faucet. Okay, so who's playing Pokemon Go? Okay, so G is the gate, which is the control part of a switch, or a valve in this case. Source is where the stuff that wants to flow is going to flow from the source to the drain, and is controlled by the gate. Is that okay? So this is where you attach to a pipe, okay, where you get water from. This is the outlet of a faucet, and this is how you turn it on and turn it off. You open the valve to let flow through. You close the valve to stop the flow. Is that okay? But there are 2 types of transistors. So let me make so you can select the whole thing, Control D to duplicate, and once you duplicate, you can move the duplicated portion. Okay, I screwed up here. Let me do it one more time. Control D, and then, okay. There we go. All right. So you can see how there's a little bubble here. Now, on this one, I'm going to change one thing. If you select a component, like a transistor in this case, the selection part here will give you the properties of whatever you have selected. So in this case, because I have selected a transistor, it tells me the properties of the transistor. The four properties of this particular transistor, some are really important and some are not as important. The first one is important. There are 2 types. One is a P-type and one is an N-type. So I'm going to change one to N-type. And can you tell me what is the difference between those 2 transistors? Yep. This one has a bubble, the other one does not have a bubble. Okay, very good. So in a bubble, or in this class, a bubble has a very specific meaning. It means negation. Okay? So what that means is if you're dealing with a transistor that doesn't have the bubble, it means if the gate has a high voltage, it connects the source to the drain. If the voltage is low at the gate, it turns off and there's no flow from source to gate anymore. That's without a bubble. So what do you think the bubble means in this case? Exactly. Low voltage at the gate turns on the device and flow is allowed, and a high voltage at the gate is going to turn it off. In other words, it's just a polarity of what turns on the device. Is that okay? Are we good so far? All right. But then you can say, but Tack, I don't understand a word that you just said. Can you show me how this works? Okay, so I'm going to move it around here so that I have a place to demonstrate the additional circuit. So there are two different circuits here. If you click on this one is a P-type transistor. If you click on this one, this is an N-type transistor. So let me make it very clear which one is which one. Okay, this is a P-type, and this is an N-type. So now the question is, what do you think are the differences between these two other than whether high voltage turns it on or off? What do you think the P and the N comes from? Yep. Positive and negative. And negative, okay? So, and in the real circuit, now we need to, the source and the drain are now different, depending on whether it's a P-type or an N-type. If it is a P-type, the source is a positive potential. Okay? So the flow is going from a positive higher voltage to a lower voltage for a P-type transistor. What do you think an N-type transistor is going to do? It's exactly the opposite. The source is a more negative electrical potential, and the negative charge is going to the drain. Okay? So let me say that one more time. A P-type is going to control the flow of positive charge from the source to the drain. An N-type transistor is controlling the flow where the source is the negative charge going to a less negative place. Is that okay? So if you want to, you can kind of document it like this. The source is a source of positive charge in this case. The source in this case is the source of a negative charge. Are we good so far? So they're still just valves, okay? They're really just devices that can control the flow of something. In this case, they're controlling the flow of charge. One controls the charge of positive charge, and the other one controls the flow of negative charge. Is that okay? All right? Okay, so let's go ahead and build some circuits with these transistors. So I'm just trying to think. I'm thinking about whether to give you the final design that I want to work on or whether I want to use an intermediate design. Let's go ahead and start with the actual design that I want. And so this is how you make a new design in LogicSim. And we'll get a few of these things. You can rotate these. Oh, by the way, what is phasing? So phasing in this particular case is the phasing of the drain. Okay, so it's always referring to where is the drain. The drain is now facing east. So if I want this thing to be rotated 90 degrees clockwise, how do I change the phasing? Yep. So you can now change, I think you can select both and change the phasing at the same time. There we go. I also want to change this one so that the gate is not pointing to the west. I want the gate to point to the east. What property should I change to make it go that way? Gate location, very good. So I can switch the gate location just for display purposes. Okay, it doesn't really change the way it works, it just looks better this way. All right, so I'm going to need 2 more transistors. So here's one, duplicate another one. And these 2, I want them to be N-type transistors. So I can select both, change the type both to N-type, and I want to rotate both of these so that the drain points north. Okay, so I need to change phasing to north. And we'll go ahead and put one here, and then we'll put one here. Okay, so now we got the basic design of what I want to show today in class. And then the other thing we need to now put into the design would be an infinite source of positive charge and an infinite source of negative charge. Has anyone taken circuits? Okay, some people have. So how do we call the source of negative charge in a circuit? Negative terminal. In this class, we just call it ground. Okay, so ground, this particular symbol, basically represents an infinite source of negative charge. Is that okay? And there's a symbol for the positive charge as well. It's power. So this is the symbol for the source of an infinite amount of positive charge, like so. Is that okay? So what we'll do is we will start to make connections. Yep.
Wait, what is that called? The thing on top of it?
It's power, which is also known as power supply or voltage supply, supply voltage. Okay, so I'm going to make a circuit here. To draw a connection, you just have to drag a wire around until it makes connections. Now for this one to make a connection, it's going to form a little bubble here, which means there is contact between the positive voltage source to this particular wire. These 2 will meet as well. Okay, and then this one goes here. This one goes here. Okay. It just looks ugly, but it was functional, but it just looked ugly, so I had to change it. There we go. Okay. So now we have a kind of more interesting circuit. We have one single source of positive voltage. We have one single source of negative voltage, okay? And then we have a bunch of switches or valves in between. So you can kind of imagine if I turn on every single valve, we'll just have a lot of electrons, flowing from here to there, okay? Which is kind of not what we want. Because if I did that, okay, so can anyone tell me what's going to happen when I turn on all of the valves so that they all allow flow to go through? What's going to happen? It's a short circuit, okay? And what does a short circuit do? It blows up stuff. Okay? Because you have a huge current. Basically the current is going to go from the positive voltage to ground, and because the resistance in between is very low, you have a very high current, and then you have, when you multiply resistance with current, you get a voltage drop. When you multiply voltage drop to current, you get power, okay? So that's basically all heat. So all of these transistors will die and get vaporized in the process. So we don't want to turn on all the switches all at the same time, okay? So what we'll do is now we will start to have terminals. So these are terminals for input and also output. The square is the input, the circle is the output. So I'm going to have 2 input pins, and one single output pin, like so. The output pin is really just sampling the voltage at this point here. The input pins, on the other hand, would be connected to gates of the various transistors. So these two transistors are connected to the same pin. And I'm going to move this one down a little bit just so that it looks nicer. This input pin is connected to this particular gate, and it is also connected to this one over here. All right, so now we have a circuit, okay, that's made out of 4 transistors. Does it make sense? If both inputs are low, 0 is low, 1 is high, that this will experience a high voltage. Does that make sense? Can I answer your question? Okay. So tell me again, how do you turn on, oh, by the way, is this a P or an N transistor? It's a P transistor. The P transistor has a bubble, okay? It allows what kind of charge to flow through? Positive, okay? And it's always going from which terminal to which terminal? From source to drain, okay? Where the arrow is indicating the flow direction. What about these 2 transistors? What type are they? N transistors. With an N transistor, what kind of flow are we talking about? Positive or negative flow? Negative flow. The negative flow is flowing from the source to drain. So the arrow is correct again. Is that okay? Because this is where the negative charge is. That is where the positive charge is. So the transistors are oriented correctly, even though they look kind of strange because one is pointing down, the other one is pointing up. Is that okay? So let's focus on one particular switch first, or one particular wire. We'll focus on this one here, okay? This is a low voltage. Does a low voltage turn on a P-type transistor, or does it turn off a P-type transistor? Does it allow flow with a P-type transistor? It allows P-type transistors to allow flow, okay? What about an N-type transistor? Does it allow flow with an N-type transistor? It stops that, okay? Okay, so that means with only the wire that I'm highlighting, it is allowing positive charge to flow from here through the transistor to this junction here. But at the same time, this is turned off. It is not allowing flow. Is that okay? Let's look at the other wire. Let's look at this one. It's symmetric, right? So once again, because it is low, it is turning on the other P-type transistor. We are allowing flow from the positive charge through the transistor to the output pin. But when you look at the transistor at the bottom of the whole design, this is an N-type transistor, which only turns on when the gate is a high voltage. But the gate is a low voltage, so it's turned off. So that's why both transistors, both N-type transistors, are turned off. They are not allowing flow. Yep?
How do you know if it's a low voltage?
If it's a 0, it is a low voltage. If it's a 1, it is a high voltage.
Okay, and you set that when you put the pins?
Yep.
Okay.
Yep. So 0 is low, 1 is high. Okay? So does that explain why the output pin is a 1, why it is a high voltage? Because it has 2 paths to the infinite source of positive charge. Is that okay? What if I turn one of them on? Okay, if I go to one of these pins, and by the way, you can change the state of a pin when you're using what they call the poking tool. So when your mouse pointer is a finger, it is called a poking tool. Okay, so the poking tool has 2 main purposes. One, it allows you to highlight a particular wire. The second one is it allows you to change the state of an input pin. Okay? Okay, so does this picture make sense? Let's try to figure out. This is a high voltage. It goes into this particular P-type transistor. Is it going to turn on the P-type transistor or turn off the P-type transistor? It's going to turn it off, okay? And it goes here to the N-type transistor. Is it turning on the N-type transistor or turning it off? Turning it on, okay? So we have, okay, let me use the mouse pointer here. So this transistor is now off. This transistor is now on. But we have the other two transistors. And the gate voltage of the other two transistors is still a 0 in that case. So this N transistor is still off. Okay? Now, the two N transistors are connected what we call in series, which means if at least one of them is off, then the whole thing is off. Does that make sense? Okay, so that's why we still do not have a path from the negative charge to the output pin because one of them is off. This one is off. Is that okay? Even though this one is on. Yep.
That's why it explains why high voltage turns on the P-type transistor, because they're series.
Well,
Because the left one is on right now. It should be on.
the left one is off. This one is actually off. But this wire is still experiencing a high voltage because of the other transistor. Because this particular transistor here, this one here, is now on. So it is still completing a path. So there is still a path from the high voltage source here through only one transistor in this case to the output pin. But the low voltage has no way to connect through here because one of the transistor, naming this one here, is still off. So that's why the result is still a 1. Is that making any sense? Now, if I change this one to a 0 and this one to a 1, it's going to be the same thing because the left-right transistors are symmetric. And then the bottom two N transistors are also quote-unquote symmetric in a way because you need both of them to be on to allow flow from ground or the negative source to the output pin. So the next configuration we want to look at is when both inputs are 1s. Like that. Oh, the output finally has changed. But why is it changing? Well, let's try to figure it out. What turns off a P-type transistor? What kind of input at the gate? High voltage, a 1, right? Well, we got a 1 going here, and we also got a 1 going here. So now both P-type transistors are turned off, not allowing flow from the positive charge source to the output pin. What about the N-type transistors? They turn on when the input or when the gate has a high voltage. Well, there's a high voltage here, there's a high voltage here. So both of the N-type transistors are now turned on, allowing flow. Because they're connected in series and they're both turned on, we now have a path from the negative source through both of the N-type transistors to the output pin. So the output pin is now a 0 because it is connected through the two N-type transistors to ground. Is that okay? Are we good? All right. Yep.
Why is it 0 when it's connected?
Ask the question again.
Why is it 0 when it's connected and 1 when it's not connected?
It depends on which side is connected. So right now the output pin is connected through the two N-type transistors to ground, and ground is 0. Yep.
So does that still represent low voltage for 0?
Yes, 0 is still representing low voltage. Yep.
And if we get rid of the ground and leave the two input pins, what happens?
Say that one more time.
If we get rid of the ground part,
If we get rid of the ground, get rid of this symbol here, then it has no place to connect to, so the output would now be undetermined. Is that okay? All right. So if I label these things a little bit, okay, I'm just checking the time. The class ends now, right? Okay. Your lab, this is kind of what your lab is about. Okay, your lab is to design something like this. So we're going to head out to the lab. And I have to turn off.